Hello everybody, in this video we're using Ansys Fluent to perform a steady state turbulent analysis over a backward facing step. So this is a classic turbulence test case, experimental and numerical benchmark test case. So this is the first time we're going to look at the use of turbulence as well, or turbulence modeling. So this test case is also described, and there's a set of slides uploaded beside the tutorial. So we can look at this in later when we get to OpenFOAM as well. So it was run by these people called Pitts and Daly. They ran an actual experiment. So they had flow coming into this geometry here from the left. So it goes over a step. So you get a large recirculation zone here. And then the flow, eventually the streamlines reattach to the bottom of the domain. So if you plot the streamlines, they're following the wall, but then they detach from the wall here, and then they reattach down here. And they measured this, the distance to this reattachment, and that's often used to benchmark turbulence modeling approaches. So the velocity is quite high, and so a lot of turbulence in this case. So if you go through these slides as well, it's going to talk a little bit about something known as wall functions. So when you've turbulent flows, well, as you get very close to the wall, because the wall's slowing down the flow, you'll always have a laminar region very close to the wall. But depending on the size of your first layer of cells, your first cell may be in the turbulent region, or in the laminar region, or in what's known as the buffer region. So there's different ways to deal with that in turbulence modeling. So there's something called wall functions, and I encourage you to read through this to get a feeling for what they are and how they're used. But the solution that we're expecting will look something like this. And from the experimental paper, they found that if this is the step height is h, they found that the reattachment occurred at approximately 7h, or 7 plus and minus a half h. So the equations we're going to solve, it's incompressible and Navier-Stokes equations like before, but now we're going to introduce a RANS turbulence model. So in this case, we're just going to use the classic K epsilon one. It's not necessarily the best one, it's just a classic one. So we'll stick to that. Okay, open up Workbench. Let's save our model. I'll call this Pitts Daly, just after the author's case. Save it. Okay, I'm going to drag across a Fluent analysis system here. You could do a component by component. Call this steady state. So a second follow-on part is you could try run this as a transient case as well. You could either read a U-RANS, an unsteady RANS, but that wouldn't probably show very much, but you can do a DES or a detached eddy simulation as well. So let's go straight into opening geometry. You can set it to the 2D over here, although it would pick that up if you draw your model in 2D anyway, but we'll just set it to force it to be 2D to catch any errors. We'll double click here and wait for SpaceClaim to open. Of course, like in all models, you could right click and you could import your geometry here from another CAD package. Okay, when SpaceClaim opens, we want to sketch on the XY plane, so we're just going to flip the sketching plane. So like before, left click on the y-axis, then right click and go select a new sketch plane. And then just wiggle your mouse around until you get it in the right plane, and left click. Change the view over here to be front. Okay, so now we're going to start sketching. So for the step, the inlet, we're going to have the bottom of the inlet here, and then the channel is going to go like this, and then we'll have our step here. So we'll have our origin just there. You may want to set the default dimensions in SpaceClaim. So if you go File and SpaceClaim Options, there are units here. So you might want to set the default dimensions to be meters instead of millimeters. So in this case, I'm going to set them to be meters because I'm going to draw everything meters. It can be picked up later and changed in Fluent, but I'm just going to set them here. So you'll see there's multiple ways to set the same thing. Okay, I'm going to draw a line. So we can either click and hold and drag, or I can just click the first point and then click the center point. So before clicking the center point, you can see it is actually letting me type distance. So in this case, the first line is 0.0 0.0206 meters. And press enter. So then it's going to let me draw the next line. So I'll just go down vertically. And the step height is 0.0254. Press enter. We'll go across this way vertically or horizontally. Make sure it's at 90 degrees. And the length of this is 0.206. Press enter. It's going to reset the view. The angle here, I'm not sure what the angle is, so I'm just going to click anywhere and then I'll set the dimensions afterwards. So I'll click somewhere there, and then the height of this outlet is going to be 33.2 millimeters, so 0.0332 millimeters. I'm not too worried. I want to line that point up there vertically with that point, but the angle I'll fix afterwards. So I'll click there, bring that over to line up there, and click it back to the inlet. Okay, so I'm just going to finish by dimensioning the rest of the parts. So I'll set the dimensions of this line here. So the step height and this inlet height are the same. So then hover over this, when it's purple or blue, click on it. You'll see you have a cursor and you can just type. So it'll be 0.0254. Press enter. So you can see that's the same height as that. Let me check. That looks suspicious, as if it may have moved. So I might just check the length of this line here as well. Yeah, it looks like it didn't preserve my original dimension. So I'll click on that and set that again to be 0.0254. So you can see, I think for displaying purposes, it's just rounding the numbers. Let me just check this distance is correct as well. So that I think is correct. It was 0.0206. Press enter. And these distances should be correct. And this should be correct. I want to center this point. So I'll click the point there and then click the line. That will just set the distance. Click on dimension again. So it's going to be perfectly centered, the outlet. So half of 33.2, so 16.6, so 0.0166. So I'll make it centered, and then the only thing is set the angle, but I'm going to set the length instead. So I click the dot here and the dot there, and go down this way and set that horizontal distance to be 84 millimeters, 0.084. So a long outlet. So let's just reset the view. Okay, I think we are ready to go. So I can end my sketch now. So we want to use a structured mesh in this case. So to use a structured mesh like a perfect grid with squares, that typically will mesh is only smart enough to do that if you split your geometry into 4-sided parts in 2D or 6-sided parts in 3D. So then, for example, if there's a small cube here, it will know how to put a grid on that. So to help the measure, we're going to split this part. So if we click on split here, we're in the design tab. And we have an option here that we can select this face. And if you just select this corner here, that will split this into 3 faces. Now we have a 4-sided little block there. And this one is kind of 4-sided, but there's a kink there, so maybe we'll split that as well. So we select this region and holding, let's press escape actually, split, and then hold control, select the first and the second. And now if we select just there at the corner, that will split across there. So now we have a 4-sided part, 4-sided part, 4-sided part, 4-sided part, and 4-sided part here. So then the mesher will be able to easily put a grid on this. Using the split tool, it is possible after you click on a part to split it, you can split it by a line if you've sketched lines as well. So you can sketch, it doesn't have to be perfectly vertical lines here. In this case, we did have vertical lines. I'm going to add some named selections as well. So I'm going to define my inlet. So left click here, create name selection, inlet, center, left click, and then holding Control, select both of those edges, create name selection, outlet, center. You can do this in the mesher as well. I'm just going to do it here for a change. So now select the walls. So there's 3 patches: inlet, outlet, and walls. So left click there, hold Control, click there, 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 there. So now we've selected all the banner. And we're going to call that walls. Center. So now we're done in Space Clean. So we're just going to close out of this, and we're going to go on to the mesher. So you can just double click, open the mesher. And I'll pause the video because the mesher seems to be always the slowest part opening. It often takes 30 seconds to a minute to actually load the geometry. Okay, so our mesher is now open with our geometry. So you can see we have our named selections, and the mesh has to be created. So let's just set the default element size to be 1 millimeter. But now we're going to also use well, one, we're going to specify to force it to be structured mesh. So to do that, we're going to click this face meshing. So click face meshing, and then if I click on one of these, it goes green. So holding Control, then select all 5 blocks. Go back to the yellow part, click on that, press apply. So we're setting that to mapped meshing. So mapped meshing means structured meshing. So it's going to make like grids in each of these blocks, and they're going to be quadrilaterals. So that's fine. The last thing we're going to do in the mesher is, because it's turbulent flow, the boundary layers are going to be quite thin. So at a physical wall, the velocity is 0, but then within the flow, it's obviously non-zero. So you'll typically get a profile, like a logarithmic profile of the velocity going parallel to the wall. So on the turbulent flow, this layer would be quite thin. So I'm going to refine my mesh to make the cells smaller near the walls than in the main flow to try better capture this. So to do that, I'm going to use sizing. So sizing just lets us locally set like the seeds, as Abacus would call it, or the cell size. So I'm going to do it just on the edges. So make sure that our edge selection tool is selected here. So you can see a little green edge selection. You can hover over it. It says that's for selecting edges. This is faces, edges, points. So edges. So I click on this inlet and holding Control, select all these vertical lines. So 3, 4, 5, 6, 7. So go back here, press apply. The default element size, we can leave it as 1 millimeter, as already set. So you can see it's actually sketching the element size, so we can see. So that hasn't changed anything yet. The default was already 1 mil, but I'm going to create a bias. And so bias is called a grading in Abacus. So that's just setting the ratio of element sizes from, say, near one end of the edge to the other end of the edge. So these little lines are meant to represent, say, big to small, or small to big, or small to big to small, or big to small to big. That might sound a bit confusing, but if I select this one that has a little dash, and then pick up a bigger dash, and then biggest dash in the center, and then create smaller again. So that middle one. So that's going to put small elements or cells near the both ends of each edge, and then larger ones in the center. So that will better capture the boundary layer. So to find the factor, let's set it to 5. So this is the ratio of the biggest to the smallest. So if you can see here, you now have very small elements or cells near the wall, and then larger ones in the center. Okay, we probably didn't need to do it on this one because this is actually a wall, but okay, it's fine the way it is. And you can see when it's a mapped mesh, it'll follow the whole way through. So it's fine for that sizing. And now we're going to set some sizing in the other direction. So click make another sizing. That's going to be an edge sizing as well. So make sure it's selected on edges. And we're going to click these 3 horizontal lines. So holding Control, select those 3, press apply. And default element size can be 1 millimeter again, center. And we're going to have a one-way bias here. So it's going to go from small to big, the second one. So if we just check here, we need a factor. So our factor will be 5, center. So if you see here, the bottom one is the correct direction. It goes from small to big, but the other 2 are flipped. It's in the wrong way. So to reverse that bias or to flip it, just click on this last one here, and then left click on the first line, and then control click on the second one. And I just press apply and that will flip those. So you can see all three now are small on the left, big on the right. So we're just trying to capture the larger gradients in velocity that will happen here just as the flow goes around the step. So just as it passes the step here, you get a separation of flow, and the flow here is going in one direction, the flow underneath is going the other direction. So we just want to capture those high gradients. We want to have fine cells around here. Okay, we're ready now. So click on mesh and either just click generate the mesh or update. Does a few extra things, and we're going to have to do that anyway when we go back. So it's probably better to just update it here. So that's our mesh now. So you can see that we have nice fine cells near the wall and relatively fine cells around here as well. Okay, so that's us done in the mesher. Next on to Fluent. So you can see we have a green tick now. So double click on setup and we'll open Fluent. Double precision or not. If you're not sure if it makes a difference, then you can run the model with and without and compare the results. That's often the case for many settings in modeling. So I'll give it a second to open. Okay, so let's just go from top to bottom on the left here. So we're on general. Let's just check the scale makes sense. So yeah, everything's in meters and it's the right distance, but you can see we could have changed it here if we had done it in the wrong dimensions, the wrong scale, or maybe if you want to switch from millimeters to meters. Click check to see it's happy. The graphic here looks okay. It looks like there's an inlet and outlet correctly identified. So it's going to be steady state, 2D planar, pressure based. The only reason you might switch to density based is when you have a compressible fluid. It may be more efficient or stable to use density based rather than pressure based. So we have no gravity. Next onto the models. So click on models. You can either click here or over here. So go to viscous behavior. So in previous tutorials we've used laminar, but now we're going to do turbulence. So there are many turbulence models, and if you look at the turbulence lecture slides, you'll see of the different types of turbulence modeling approaches. So let's say the most inexpensive is a RANS approach, the Reynolds average Navier-Stokes approach. And within RANS, there's a couple of types. So one approach is called the eddy viscosity approach, where it simulates turbulence by locally increasing the viscosity in some way. And one of the classic ones is called K epsilon. It defaults to K omega SST, which let's say is a more state-of-the-art law. It typically works better than K epsilon in most cases, but we're just going to stick with standard K epsilon. There are a variety of K epsilons as well. So as you imagine, this is like an active research area. So people are always trying to improve turbulence modeling approaches. So if you do plan to use any of these, then do read up in the documentation about what they do and how they change the modeling behavior. Also, for these wall functions, it uses standard wall functions by default. So they pretty much they're only great when this y plus value is between 30 and 300. So if you're maybe less than that, between 5 and 30, this is called this buffer region, then it might be better to use these enhanced wall treatment. We're just going to leave the standard one for now, but we'll have a look at that as well. We'll just use the default values. So standard K epsilon and standard wall functions. Let's go into our materials. So it's set to air. So they did use air in Pitts Daily, but I think the air was a slightly colder temperature than the default here in Fluent. So it was a little bit denser. So I'm just going to change it to the values that they were using. So 1.293, and also it was a little bit more viscous. It's only by a very small amount, but we might as well use the correct values. So click change grade. So 1.81 e to minus 5 for viscosity and 1.293 for the density. So I'll close. Cell zones, fluid. Just see it has the correct name. So it's air. The name here, that just came from the measure or from space claim. You can change that if you want, but this is all fine. And close those. Boundary conditions next. Double click. And we have our interior domains. One of these, I can't remember which, just represents the internal line, so they don't do anything. Inlet is a velocity inlet. I'm going to edit that. So the incoming velocity they used was 10 meters per second. So I can just press apply. So we're not going to have a parabolic profile because there wasn't a parabolic profile, and it was an incoming turbulent flow. So the true experiment, you can find the original paper, and it's a much bigger system. This is just the experimental chamber, so you could model the full system. But basically, the average velocity was 10 meters per second coming in here, and the boundary layers were very, very thin, so we're not going to prescribe those. Now that we're using turbulence, we actually have to specify something about the incoming turbulence as well. So there's different ways to do that. We're using K epsilon. We could specify K and epsilon. So K is the kinetic energy of the turbulent eddies. So the eddies that we're not directly simulating, the ones that are, let's say, smaller than the mesh resolution. And then epsilon is the rate at which those turbulent eddies just dissipate into heat, for example. But they're not so easy to physically define. You can look up the formulas for them, but it's easier just to specify the intensity, the turbulent intensity. So turbulent intensity of 5% would mean 5% of the mean kinetic energy of the flow is in these small turbulent eddies, or eddies or vortices. So that's generally quite high, but that's fine in this case. And the turbulent viscosity ratio is the ratio of this turbulent viscosity, which is like a modeling viscosity. It's not a physical viscosity, to the real dynamic viscosity. So that's fine. It's not too high. You'll see it'll get much higher than that in regions of high turbulence. So that's all fine. It's normal to the boundary. Our walls will be just stationary, no slip walls like before, and nothing to change there. And our outlet is a pressure outlet. That's fine. So we're good with the boundary conditions. Keep going down. Reference values, we're not going to print out force coefficients or anything here because we're doing just an internal flow. We're not looking at flow around something, or like if you're doing aerodynamics of a car or a wing, you're interested in the drag coefficient or lift coefficient, but here it's just internal flow, so we don't care about those things, so we just leave those values. We're not using them. Yeah, okay, so that's our setup done. Onto the solution. Methods, I'll come back and check, but the default now is coupled. Only a couple of versions ago, so we're on 2020 now, but 2019 or 2018, the default was actually simple, which is an acronym. So we'll just check how that affects it. Typically, the coupled one is more robust, and it's probably just the best one to stick with. You'll also notice now that we turned on turbulence, there's some extra options. So there's first order upwind and first order upwind for the two extra equations that are being solved. So the K equation and the epsilon equation. We can leave them all for now. Typically, if you're running a RAN simulation, especially if it's a complex case, this is not so complicated, but if it was a real complex case, you might set all of these to lower orders of accuracy, first order, just to get an initial answer. And then you can restart the case using higher order schemes. So that helps them converge. So if you use higher order schemes, sometimes they don't converge. The residuals just don't converge. So you need to start with lower ones and then change to higher ones. But we'll just leave them as they are for now. Monitors, anything else we need to do here? No initialization. We can just give it a hybrid, default hybrid, that's fine. It'll do something smart for us. Nothing here, it's just steady state or run calculation. Won't need 1,000 iterations, but I definitely just wanted to converge, so I'm going to set it to a maximum of 1,000 to calculate. Also, in this case, this Pitts daily case can be a little bit sensitive, the reattachment point, to the solution tolerance. So we've left the solution tolerance at the default, which is 1 e to minus 3. So all these residuals will try to get beneath 1 e to minus 3. But it can be sensitive to that, so that position might change as you go to 1 e to minus 4, 5, 6. So that could be something to check. So a few things are different here. Like before, we have the continuity equation being solved, and that is the last one to converge. We also have the x and y velocities, so they're the momentum equation in the x and y direction. So there are 3 solved. Then we have 2 extra ones. So there is a scalar K equation and a scalar epsilon equation, and they're the 2 turbulent equations for this eddy viscosity approach. So you can see they also converge down. So in this case, you can see we've 5 scalar unknowns in a 2D RANS simulation. So if we go to 3D, we'll have the Z direction as well. You'd have 6. So that's fine. Let's converge. Let's go look at some of the results. So we'll go graphics, double click on contours. pressure to default. Let's just display that. So that's fine. Let's look at the velocity. So the velocity coming in, see it's all 10 coming in, and you can see if you zoom in with just the mouse, the boundary layers are really, really small. So they're probably within the first cell. And then you can see what happens here is it just gets detached. So it'll be more clear if I look at the path lines. So if I go look at path lines here, released from the inlet display. Yep, it's fine. So if you see here, you can't even see the step. So the streamlines just go straight over the step, and then they'll reattach at a point over here. So we can use CFD pose to try and measure that a little bit more accurately. So that's fine. A couple of other things to look at here. If we go back to contours, under velocity, anything here. So you can use things like the Q criterion or the lambda squared criterion to identify vortices, but it won't show very much in this RANS case. It's more for transient cases. But what is interesting is if we go to the turbulence drop down, so you have another turbulence one here. So we actually have K and epsilon. We could look at K and epsilon. So if we just display K, so what K is showing is, this is showing where the kinetic energy of these small turbulent eddies are. So the RANS approach isn't trying to calculate where these eddies are, it's just calculating the average velocity flow field. But in reality, if you actually ran this experiment, you would have like different, maybe periodic or non-periodic vortices forming and dissipating and breaking up. So this is predicting that you get high intensity of these in these regions. And then if you look at epsilon, well, once you have that kinetic energy in these eddies, then those eddies will just, the larger eddies break up into smaller ones, which break up into smaller ones, and they keep breaking up until they get to the Kolmogorov scale. And at that point, when they're very small, they just get dissipated into heat. So these regions here, these red regions are where that happens. So it's pretty much near the walls is mostly where that happens. So here, because you have these essentially laminar viscous layers in the boundary layer, that the energy gets dissipated there, and just some here as well. And you can also look at the turbulent viscosity ratio. So this is the ratio of the turbulent viscosity, which is this artificial viscosity that the RANS approach uses to simulate this Reynolds stress, relative to the default material viscosity, dynamic viscosity. So you can see it goes up to almost 400. So this region of the flow, from a macroscopic perspective, it's like it's 400 times more viscous, just because there's so many of these eddies being mixed together. One other thing to look at here is the wall Y plus. So the wall Y plus, so Y here represents, if you imagine you have a wall in the X direction, and Y is the normal to it. So it's the distance away from the wall. So you could say what the Y is, and by Y is the distance from the wall to the first cell center. And you're interested in knowing that relative to the boundary layer of the incoming flow. But that boundary layer will depend on the velocity of the incoming flow, or the Reynolds number of it. So this Y plus is basically like a normalization. It's kind of like a mini Reynolds number. So it's taking the Y and it's normalizing with respect to the energy of the incoming flow, the kinetic energy. So it means that we can use this Y plus to compare different geometries with different Reynolds numbers, and it still works. So Y plus is like a dimensionless measure of how far away the first cell center is from the wall. So if we zoom in here, it's only defined on the wall. So you can see it's, what's that, 13 here. So we're using standard wall functions. So they really are only accurate if the Y plus value is between 30 and 300. So in this region here, it's probably better to use enhanced wall functions. You could just rerun this with enhanced wall functions and just see the main difference. You can see though, even though the cell size could be the same, it depends on the y plus, depends on the velocity of the flow. So you can see down here we have much less than 5. So like even less than 1. So all the wall functions approaches would typically, in Fluent anyway, should give the same answer if your y plus is less than 5. And essentially enhanced and standard wall functions will give the same greater than 30, but in between 5 and 30, then maybe enhanced is better. So it might not be a bad idea to use that as a default. So now just to check, I'm going to go back and see the effect of using a simple solver instead of a coupled solver. So if we go back to initialization, so I'm going to reinitialize the flow. So just overwrite the current solution field, go back to run calculation, actually go back to methods and change it to simple. And simplex is just another variation of simple. And go run calculation and check case. Oh, it's giving some recommendations here. Consider realizable k epsilon in lieu of the standard. So it's basically saying that the standard k epsilon model, it's maybe better to use the realizable one. It's a little bit better. So we're just going to keep with the classic one for now. So this is the simple solver as opposed to the coupled solver. So there's a couple of things you'll notice. They're a little bit subtle. One is each iteration is a little bit faster in simple than a coupled solver. So just to do one iteration might be faster in simple than a coupled solver. But that might be not so important here. The more important thing is the residuals tend to converge slower using the simple solver. So if you remember, we have to get everything down to 1 e minus 3. But as of now, if you look at our continuity equation, and the residuals, they're not converging so well at the moment. The other ones are going down. So I can't remember how many iterations it was. You can skip back in the video. It was probably like 100 or something like that, I think, for the coupled solver. So the simple solver is not as smooth a conversion. So it even started the diverge there, and now it's coming back down. So it's basically iteratively updating the velocity, pressure, K, and epsilon field, and trying to find the answer to correctly satisfy the discretized equations. So if we wait, I'm going to pause the video and see if it converges. Okay, so it's just coming to the end now. It's coming to 1000 iterations, and it's almost going to get there, but not quite. So if we looked at the residuals, we almost got to 1 e to the minus 3, and they're quite noisy. And if I scrolled up here, I should see the last residual. So this first one here is the continuity. So I'm trying to get to 1 e minus 3, and I got to 2 e to minus 3. So it wasn't too far away. But you can see in this case, it actually was much less efficient to use the simple solver than the coupled solver. So the answer is, assuming we're hitting the same tolerance, should be approximately the same if that tolerance is tight enough. And one other thing to note is simple foam, or not simple foam, sorry, the simple algorithm will use much less RAM than the coupled one. So that may be a concern. I'm not monitoring my RAM here because it's not so big a case, but if it was a bigger case, the coupled solver tends to use much more RAM. So it could be a factor of 5, for example. If I just have a quick look at the contours, and say velocity again, it should look the same in this case. There isn't really anything to see. Let's jump over into CFD post just to do a couple of last measurements. So we're just going to generate some extra streamlines just so we can see the actual recirculation zone and try to more precisely measure this reattachment point. So when it loads, we're going to click on Z to look in this direction. So what we're wanting to do is generate some streamlines. So we can do that over here. We can do it here as well. So insert streamline. So we can call it streamline 1, that's fine. So start from the inlet is fine, 25 points, forward direction press apply. So this is kind of what we got already in Fluent. So you can kind of see the reattachment zone, or reattachment region. So what we might do here is add a line maybe here, and then we can have the streamlines start from that line, so we can definitely get some points in here. So let's go insert a location and a line, and we call it line 1. So coordinates, you can either drag here to go like to the extent of the domain, or I think a value of maybe 0.1 here, and then I'll put it at the bottom of the domain, then skip around 0.1, and then the top of the domain maybe. And probably is okay. So let me go back to that streamline here. Streamline 1, double click on it. Instead from the inlet, I'm going to come from line 1. So if you see line 1, there is that yellow line here. So if I start from that, press apply, so you see a couple of things. So it starts a bunch of streamlines here, they just flow straight out of the domain. But in this lower velocity region, anyone that starts, they just keep going round and round and round and round. So it might be good that we could add maybe 2 sets of streamlines to really pick up, let's say if you want to create a nice picture of uniform streamlines, you might put this line only from here to here, and maybe only have a few points, and then you could have another line here, or just from the inlet to get the other points. But this is fine for now, because if you see down here, you can actually see pretty well the reattachment is just around there. So how can we measure that precisely? So we can use a probe or a query here. So if you click over here, this little thing here, this is a probe or a query. So you can just kind of click a point maybe around here or here. It's a little bit ambiguous. So you can see it gives the coordinates of 0.19. Maybe you could say it's more like there, so 0.186. So the experimental answer for this daily was, I think, was 179 or something, plus or minus a certain distance. So we're pretty close to that at the moment. And so I'm going to jump back out of CFD post, and I'm just going to briefly look at in Fluent. If I open up Fluent again, and just going to look at, well, how we might change it to a transient case. So often if you're looking at a RANS model and RANS works okay and you're just trying to get it more accurate, and there's a couple of options. So you basically start looking at turbulence modeling, what are the maybe the more advanced turbulence modeling approaches. So one is if you stick with RANS instead of K epsilon. As we saw, there's a variety of K epsilon models, or there's other eddy viscosity models that you could use. So let's just change this to transient models, discuss models. So you can look at different wall functions and different types of K epsilon. There's also K omega, often is better as well. And there's other types of approaches here. Separate from eddy viscosity RANS approaches, there's also something called a Reynolds stress approach. So you can see how many extra equations are added. So this is more expensive because you have 5 extra equations. And what it's trying to do here is it actually models the so-called Reynolds stress. So that perturbation term that we had from the Reynolds averaging, rather it tries to directly calculate that full stress. So it's effectively like a stress. So that's called a Reynolds stress. So it tries to model that. Convergence can be more difficult with these types of models, but typically they're more accurate than, say, K epsilon and other RANS approaches. If we go past the RANS approaches, then you can start to go towards LES, large eddy simulation. There's no LES simulation here because this is 2D, and LES really only makes sense in 3D. You can, if you look up online, there's a way to type a command in that forces it to give you an option here. But you can do detached eddy simulation. So this is RANS near the wall, and then it tries to capture, it's like LES away from the wall. So the LES part maybe still doesn't make that much sense in 2D, but we can just use it as a demonstration of how it would work if you were going to 3D. Once again, there's lots of options here. So if you're really looking at using this and understanding for your mini project, it would be good to read up on what this different option means and what's most appropriate. So it's basically built on top of a RANS model with kind of an LES component. So you have to pick the RANS model. So I'll just leave it as SS T K omega. So it's giving me some advice to do the discretization. So it's telling us that we have to use a bounded second order implicit transient formulation. So okay, let's just turn that on now in case we forget. So if we go to, I think it's methods, yeah, so the transient needs to be bounded second order. That's fine. We're going to do a transient case. Piezo was developed for transient. solutions, it's very similar to simple. Once again, coupled could be better, but typically for transient cases, there isn't that much advantage to using a coupled solver. Not always the case, so we'll use a piezo just to try it out. Once again, they should give the same answer if they converge. So let's see, everything else should be fine. We're going to initialize the flow. Rather than giving it a good guess everywhere, we're actually just going to set it to be 0 everywhere. So we're going to, if you imagine, it's like we're just turning on the experiment, the flow is not moving, it's all just settled laminar flow, and then suddenly we just turn on a big fan that starts blasting in high velocity air. So we're going to initialize that to be 0. Calculation activities, we probably want to store the velocity field to look at it. So we will go new object, contours, call it velocity magnitude, and save display. So it starts off 0, we've initialized it to be 0. So that's fine, we've selected velocity, and every time step, maybe just every 10th time step, you can change this. I just don't want to have too big a results file. So that's fine. Let's go run calculation. It's going to be a transient case now. We're going to have certain time step size. So let's think about how do you select the time step size. So we didn't really talk about that in the transient flow over a cylinder case. So how do you select that? Well, typically you think about something called a current number, or the CFL, current Friedrichs Levy number. So the current number basically says that if your current number is 1, it means that the flow is moving 1 cell per time step. So if you have a 10 meter per second incoming flow and our cells are 1 millimeter in size, then you can calculate what the time step should be to force a current number of 1. So if you calculate the current number, the formula is the distance traveled by the flow over time. So distance is the velocity by the time step over time. So you can rearrange that to solve for what the time step would be. So in that case, it's basically the distance. So if I take cell size is 1 millimeter, this is just approximate, and I divide it by the incoming flow, or the maximum flow velocity I expect in the domain. That will say that a current number 1 e to minus 4 in this case, or sorry, a time step of 1 e to minus 4 seconds will give us a current number of 1. So typically the piezo method is only meant to be used with current numbers of less than 1, say a fraction of 1. The implementation, I think, in Fluent allows you to go a little bit bigger. But we can just try it out, and you'll see if it blows up and it doesn't converge, we can just reduce it afterwards. So our time step, we're going to go 1 e to minus 4. How many time steps? I'm not going to run this till it reaches steady state. And by steady state, it's never going to just, the flow field is never going to consider it or go constant. It's going to be more like quasi-steady state. So if you actually ran this experiment and ran this model long enough, it will just always keep shedding vortices, changing around. But the RANS approach we just ran is trying to get the average of all that. So I'm just going to run maybe 100 time steps, and it's going to save 10 pictures. 20 iterations, we can set it with 100 just to make sure it converges. Press calculate. This shouldn't take too long. So it starts up. First time step, it's starting from 0, so it might take a few more iterations to converge. So it's getting there, they're kind of leveling off. Is it going to go to 100? Looks like it might. Yeah, you can see they're kind of stuck, the residuals here. Okay, I'm not going to worry about the first time step. So the first time step didn't actually converge, but it's I'm not going to worry about it too much. So now as it gets into the second, third time steps, it is actually converging. So you can see it's converging in maybe less than 10 iterations. So then after the first 10 time steps, then it saves the first velocity field. And so this tab here will be updated every 10 iterations. So you can see now it's converging. The first time step didn't converge, and they got close, it didn't converge, and now it's converging relatively quickly now in a couple of iterations. And because piezo, like simple, each iteration will be faster than coupled. If it's only taking a couple of iterations, then it's probably faster and more efficient to use simpler piezo. This is plotting total number of iterations as well, so it's not the time step. So what you will see happening here is the velocity is coming in, the flow is all stationary. As it detaches from the wall here, it starts to generate a vortex here. and that vortex starts to be pushed and extended and skewed further and further. And if you imagine this vortex is shedding off energy into smaller and smaller vortices that are trying to be captured by this DES approach. So this DES is kind of a combination between RANS and MES. So if we keep playing this on, what will happen is this vortex eventually will kind of get separated from this step, and it'll start to flow downstream. And then what will happen is another vortex will start to be generated here. So it kind of periodically starts to generate these turbulent vortices. So in the flow over a cylinder, they were laminar vortices, but these are turbulent vortices. So, okay, I haven't run it from very far. It hasn't been attached yet, but I just wanted to show you how it works. So is there anything else we can look at here? I mean, you can look at the path lines and things like that. Contours. Okay, with diesel. Let me see if I'll go to the playback here. So animations, playback, just so we can play our velocity field. So you can see that vortex is still starting to be generated, and if you keep running that on, that will become separated and more ones will develop. So if you took the average of all of this, you kept running it, then that's what the RANS approach is giving us. So we only have the velocity field stored at those time steps, but we can look at all the other fields at the last time step. So you can look at things like pressure. As before, the center of a vortex tends to be a bit lower pressure. You can look at things like Q and lambda squared criteria, so they should pick up where these vortices are. Lambda 2 might want to work better here. Yep. So if you have lots of them, you'll be able to pick them up. And then we can look at all our other turbulent things like the K and epsilon and things like that, and our Y plus values as well. Okay, I'm going to stop this video here.